Hello friends, welcome back to our channel STM Mechatronics, and in this video we will see how to configure a GPIO pin as an analog input. So this is part of the bare metal series that we are going to learn. Now the goal is configure GPIO pin. So to configure GPIO pin as analog input. So this is the main goal. So in our last video we have seen that in order to configure the GPIO pin as an input output analog, right, we need GPIO mode register. GPIO mode register, right? This register we need, and this register we need to configure, right? So this we have seen from the datasheet. I'll again walk you through the datasheet. Now, like this is 32-bit register. So bit number 31 will be the last 30. I'm going in reverse order, so I'll start from 0, 1, 2, 3, right, 4, 5, 6. Likewise, why am I underlining 2 bits? Because for each port pin, like this is for pin 0, 2 bits are used in order to configure the pin in like any one of the available mode. So this is pin 2, right? This is pin 3, and this is pin 15. This is for pin 15. So there are total 4 modes available. So depending on like the configuration 0, 0, 0, 1, 1, 0 and 1, 1. This we have seen as GPIO output. I guess the default configuration is GPIO input. This is GPIO output. Then 1, 0 is alternate functionality, and 1, 1 is analog input. Okay. So this we will confirm. So we will go to our data sheet. And in the datasheet register, we will go into the GPIO registers. Here you can see that. So this is the GPIO mode register. So this mode register, what it does is it helps us to configure the GPIO port pin in any one of the 4 configuration modes. So if you want to configure the GPIO pin as an input, we have to write 00 in the respective port pins or port pin bits. If we want to configure the GPIO pin as an output, we have to write 01 to the respective GPIO pins. And if we want to configure the alternate functionality, we have to configure it as 10 to the respective GPIO port pin bits. And we have to write 11 to the respective GPIO port pin bits. Now see, we want to configure the GPIO in analog mode. So this will be the register that we will be needing. So see, this is the register map. We have seen in our last lecture, right, that there are multiple registers corresponding to the GPIO, like mode register, output type, output speed, pull up, pull down, input data register, output data register, bit set reset register, lock register, alternate functionality low and alternate functionality high. So for this lecture, we need to configure the GPIO port pin as an analog input, correct? GPIO port pin as analog input. So we know that we have to write in mode register bits, we have to write 1 1 to the respective port pin bits. This will be for the mode register. Now we have other registers. So output type registers we don't need. Output speed we don't need. Pull up, pull down we might need. Input data we don't need. Output data we don't need. Bit set we don't need. Lock register we don't need. Alternate functionality and alternate functionality high. These registers we don't need for this purpose. So our main focus will be over here. Correct? Now let's decide which port pin we want to configure as analog input. So in our last lecture we have seen that we have used GPIO port 1, GPIO port A, pin 1, GPIO A, pin 3. One was used as output and one was used as input, but this was digital input. Now let's configure GPIO A pin 2 as analog input. So this we will do. So first what we will do is we will configure this to later we will configure pin 2 as an analog input. So we will come to the STM32 IDE. Now here we are reusing the existing project. We are modifying only what we are doing is we are modifying GPIO and we are making GPIO A pin 2 as an analog input. So what we will do is we will right click on the existing project, we will copy it and we will simply paste it. Now here we will give bare metal GPIO analog input, bare metal 3. So this will be our third project and the name, like this will be the goal, GPIO analog input, and we will copy it. Now we will close this GPIO input project. Now if you go in this project under the source directory, if you double click the main, you can see that our previous code is intact. So it will work as it is. Now what we will do is we will go into the properties, see whether the hex generation is already checked or not. In the MCU post build we have already checked the convert to Intel hex. We will click apply, and close. Now we will go to the Proteus circuit. We will do the same thing. So we have already created our circuit for the STM controller. We will copy it to the clipboard. Over here we will paste it from clipboard. Now you can see that. So in this circuit you can see that we have used PA1 as an output, PA3 as an input. Now we want to configure this PA2 as an analog input. So what we will need is we will need one variable register, right? So we have this pot HG This is a potentiometer which can generate variable output. So this output we will give to the PA2. So this output we are giving it to the PA2. Now right click, edit properties. You can see the resistance is of 1K only. Now we will make it of 10K. We will shift this. So one end we will connect it to VCC and another end we will connect it with ground. So right now we have not configured the pin 2 as an analog input. So simple thing is, now we will build our code. So previously you can see that whenever this switch was pressed, LED toggling effect was stopping, and whenever it was released, LED toggling effect was continuous. You can see that. Now once the switch is pressed, LED toggling effect stops. When it is released, LED toggling effect starts. Here, like I will tell you that even if you press this potentiometer or you vary this potentiometer, there is no effect in the toggling effect of LED or the output of the LED or any other output. Correct? So you can see this simple. Now what we will do is we will configure this port pin as an analog input. Whenever it reaches 75% of the value, maximum value, then we will start toggling of the LED, and whenever it reaches the 25% of the value, we will stop the toggling effect of the LED. So we will bypass, like we can use both the logic, but for now for our testing we will bypass this, as we have not started with our UART where we can see the ADC values. That's why I am using this option. So now we will come to our code. Here we have configured our GPIO. Okay, starting from like the registers, right? We have already given our base address, GPIO A base address, which is 4002.0000. This we have gotten from our datasheet. So if you go into the datasheet, like under the memory mapping, right, register boundary address, under this table you can see that GPIO A peripheral is connected to AHB1 bus and its address starts from 4002.0000. So the same address we have provided over here in our code. Now the mode registers, the output type, output speed, pull up, pull down, input data, output data, bit set, reset, lock, alternate functionality, low and high registers, right? These are all the registers with the offset of, like with the additional offset. So for mode register we have offset of 00. For output type register we have offset of 04. For output speed we have offset of 08. Likewise. And this information we also got it from the datasheet. You can go into the user manual. Over here you can see that this is the GPIO register map. And for the mode register we have offset of 00. For output type register we have offset of 04. For output speed we have offset of 08. Likewise. For output speed we have offset of 0.8. For pull up pull down we have offset of 0C. So you can see that for pull up pull down we have offset of 0C. For output speed we have offset of 0.8. Likewise we have configured all these registers. Now one more thing, these were the only addresses. These are the addresses. Okay, base address plus offset for the mode registers. Now we need a pointer. We need to make it a pointer register. So we can load the value into these registers. So that's why uint32 pointer. Similarly for RCC base address, RCC AHB1 ENR. So why only AHB1 ENR? That we have shown in the last video also. But I'll again explain. See, the first requirement to configure any peripheral. Listen carefully. I'll write it as requirement. So this is the very first requirement, is enable the peripheral clock. So this is the very first requirement. Unless and until you enable the peripheral clock, you cannot configure the rest of the registers for that peripheral. In our case, GPIO peripheral. So we have to enable the GPIO clock, peripheral clock, and this bit, it's in RCC AHB1 ENR. In this register, this bit is present. Writing 1 to it, it will enable the GPIO peripheral clock. That's why we have taken this RCC AHB1 ENR. Now again, you will get in the user manual and from the datasheet, you can get the base address plus the offset for the AHB1 ENR. So if you go into the datasheet, RCC, it is connected to the AHB1 bus and its base address is 40023800. So here you can see that 40023800. Now for the AHB1 ENR we have offset of 30. So if you go over here and in the clock registers, RCC clock registers, I'll expand this. RCC, I'll go into the RCC register map, right? See, RCC AHB1 ENR. So the offset is of 0x30. This is the offset. Address offset 0x30. And here the bit 0 is for GPIO enable, clock enable. So we have to write bit number, we have to write 1 to the bit 0 in RCC AHB1 ENR register. That is the very first thing. So here you can see that we have already written RCC AHB1 ENR and we have already set the bit 0 to enable the clock for GPIO A. That we have done. So our first agenda we have already achieved. So this we have already achieved. Okay, this we have already achieved. Now we will check whether we have completed this and this, correct? Now we'll come over here. So you can see that this we have already explained in the last video, how to configure the GPIO pin as an output with like pull up, internal pull up enabled, the configuration push pull and the speed as low, right? This we have already seen. some of the registers we have used the default configuration for like load speed, for push pull. Now here you can see that GPIO mode register we are configuring it for pin 1, correct? So as I mentioned, 2 bits are used for one pin. Now we have to write 0, 1, 2 bit number 2 and 3 in order to use the GPIO A pin 1 as output. So if you calculate this last nibble, it will become 0, 1, 0, 0. This become 4. So that's why it is written as 0, 0, 0, 0, 0, 0, 0, 4. So it will configure the pin 1 as an output. Now by default, the reset it is in push pull configuration, it is in low speed. So these are the default settings that we have used. Now for internal pull up, again we have to use 2 bits. So same thing we have to write. So we have seen this like the mode register, pull up register, pull up pull down register uses 2 bits. So PUPDR register, this uses 2 bits, 0, 1, 2, 3, 4, 5, 6, 7 dot, likewise if we go on. Okay. So 2 bits are used for one pin. So this will be for pin 0, this will be for pin 1, this will be for pin 2, this will be for pin 3, and this will be for pin 15. Now you can see the configuration in the datasheet. So we are using the internal pull up. If we go into this pull up, pull down, PUPDR, this is PUPDR. So we want to enable the internal pull up. That's why we have to write 10 to the respective bits of the pin. So we want to write 0, 1 in order to enable the internal pull up. So this last 4 bits become 0, 1, 0, 0, and this nibble becomes 4. So that's why it is written as 0, 0, 0, 0, 0, 0, 0, 4. So this way we have configured pin 1 as an output. Similarly, we want to configure pin 3 as an input. We will go back again to the mode register. Here you can see that in order to make the pin as input, we have to write 0, 0. So what we will need to do is we will have to write 0, 0 over here. But now we cannot overwrite this. We want to keep this unchanged. That's why we have used the AND operation. We have kept all the bits 1, only bit number 6 and 7 we have kept it as 0. So if you calculate this 3F, correct? So I'll just write the lower byte. 3F becomes 0, 0, 1, 1, 1, 1, 1, 1. This will, now I'll group it. This is for pin 0, this is for pin 1, this is for pin 2, and this is for pin 3. So if you write it, you will get 3F. And we have kept the rest of the bits as 1, 1. That's why it is F, 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 3F. Understood? Now again we want to enable the internal pull-up. The same configuration we have used. Only thing is here we have to write 01 and we have to keep this unchanged. That's why we have used OR operation, because we are setting it, and here we were resetting these 2 bits. Okay, that's why we have used AND operation over here, and while setting the pin 3 internal pull-up we have used OR operation. So you can see that we have used OR operation. This again becomes, I'll write the lower nibble only. So 0 1 0 0, this becomes 4 and this becomes, we are keeping like this we have already written, so we will write it 0 and we will simply OR it with the existing value. So this bit number 6 will be set and bit number 2 will be kept as it is. Okay. Now inside the while loop we have used some logic. We were detecting the internal pull-up. Now see, here we have to configure our pin as an, now here we have to configure GPIO A pin 2 as analog input. This we want to configure as analog input. So first thing we will need to write GPIO A mode register, correct? Now in order to make the pin as, so in order to make the pin as analog input we have to write 11 to this. So in order to make the GPIO pin 2 as an analog input we have to write 11 to this. So if you keep all those bits unchanged, if we want to keep all those bits unchanged, or simply like we want to set only these 2 pins, right? So what we will do is we will take only the last 8 bits and we will write this data. So we will have to write 0x30. So 0x00000030. So this will make the GPIO A pin 2 as analog input. That's it. It's completed. Now the next step will be, now we have configured the GPIO pin as an analog input, yet we are not using the analog functionality. So I know that GPIO A pin 2, it is used for GPIO A pin 2, it is used for ADC 0 and this is used for channel 2, channel 1 or channel 2, I am not sure, but we will see that. This is used for either channel 1 or channel 2, this I am sure. Now we will have to configure the ADC peripheral also in order to use its functionality. We'll need to configure this ADC, correct? So first we will see pin 2 is connected to which ADC. So we were at this point, we were discussing that we have configured the GPIO pin 2 as an analog input, but we don't know to which ADC peripheral it is connected. That we need to find out. Then we need to configure that ADC peripheral with certain properties. Now we need to figure out where this GPIO pin 2 is connected to which ADC peripheral. Later we will have to configure that ADC peripheral in order to get the analog input. So we will go over here. In the datasheet, we will need to search the alternate functionalities. Here you can see that it is mentioned in 401 CCU6. This is the pin names. So we have to search P, not E, but PA2. Here you can see this. The PA2, it is connected to UART 2TX timer 2 channel 3, timer 5 channel 3, timer 9 channel 1 event out, and ADC1 input channel 2. So from here we got to know that this pin, it is connected to ADC1 input 2. So ADC1 channel 2, not this. So it is connected to ADC1 channel 2, IN2 or channel 2. So this we got to know, this we have confirmed. Now we need to configure the ADC1. Again, what we will need to do is, we will need to see the ADC1 peripheral is connected to which peripheral bus. So I'll go over here, I'll check this memory mapping. I'll check ADC1, its boundary addresses, and the bus to which it is connected. So here you can see that the ADC1 peripheral, it is connected to APB2 bus, and its base address is 4001.2000. So we'll go into our code. First thing, we will define the ADC1 base address. It is 0x 4001.2000. 4001.2000. So this is the base address. The ADC is connected to APB2. So we will have to go to APB2, not AHB2 but APB2. So APB2 bus address. Again, this will be connected like this. Is the clock for the ADC peripheral. We can see that into the RCC because it is the control clock register. Now first thing we need to do is enable the peripheral clock. Enable the ADC1 peripheral clock. This is the very first thing that we need to do. Now we know that we will go into the RCC registers. We need to check the ADC1 EN. So we know that it is connected to APB1. So we will have to see APB1 ENR. RCC APB1 ENR, and in this we will have to see ADC1. So here you can see this timer. Over here you can see this ADC1 EN. So it is connected to APB2. Did I make a mistake? Yes, sorry. The ADC1 is connected to APB2 peripheral. So that's why we'll have to go into the RCC2 register, and in that RCC2 we have to go into the APB2 ENR, and in that we have to enable the ADC1 peripheral clock. Now we'll have to define this register. So the offset is of 44. So this is the RCC base address. We'll have to go APB2 ENR. We'll have to make it as unit 32 pointer because we want to write the data. We have to take the base address, RCC base address, and plus in that we have to add 44. This is the offset for APB2 ENR. Now in this APB2, first we have to dereference it. Right. Now we have to set the ADC1 EN bit. Now that bit position we have to know. So if we go over here in APB2 ENR, APB clock peripheral enable. So this is the APB2 peripheral, right? So APB2 ENR, APB2 peripheral clock enable register. The offset is of 44. So here you can see that ADC1 EN, this is bit number 8. So this is bit number 8. So we will go into the bit number 8. Here you can see that bit number 8, when we write 1 to it, the clock is disabled. So they have made a mistake in the data sheet. So 1 is like the clock is enabled, 0 is like clock is disabled. So they have made it to the entire like disabled. So 1 is enable, 0 is disable. So we'll have to write 1 to bit number 8. Again, we'll have to come over here. Okay, RCC APB2 ENR bit number 8. So I'll start from 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have to set this bit. The rest of the bits we have to keep it unaffected. So I'll write 1. Okay, and I'll consider all these bits as 0. So this become 1, this becomes 0, this becomes 0. So these are the bit positions basically. So what we'll have to do is we'll have to RCC APB2 ENR or with 0x 00000100. So this is the nibble 1, this is lower to lower byte, lower 2 nibbles, so that is 1 byte. So that this value we have to write into the APB to ENR. So that will write in our code 0x00000100. So this will set the clock for, or this will enable the clock for ADC1 peripheral. Now in this lecture we will see only till this point. In the next lecture we will see how to actually configure the ADC peripheral. So thanks for watching this video. If you have any questions regarding this bare metal programming, please post it into the comment section or directly contact me through the mail ID. This is stmmechatronics@gmail.com. So that's my mail ID, or you can connect with me on the Telegram channel. Thanks for watching this video. If you like this video, share with your friends and subscribe to our channel. We'll see you in the next video.